What's up everyone, and welcome to this video about PID or PID controller. And in this video we're going to talk about what this is and what it stands for and why you want to use it. So to start off, what the actual naming here is, PID. It's short for proportional, integral, and derivative terms. And yes, what does it mean? And I'm sure maybe you've heard of these terms before, but some of these terms might be new to you, and don't let that frighten you. We'll go through everything basically. So when you watching this, you're gonna need to have some programming skills, and I'm gonna assume that you have at least some kind of programming knowledge for doing this. If you don't have, I mean, I'm sure you can follow along anyway, but maybe the demo isn't as productive for you, and you can just skip the coding part of it anyways. And if you know Python, good for you, because that's what we're going to be using. And if you know game physics, also good for you. If you know how to do arithmetics with vectors, also good for you. If you know linear combinations and what that is, good for you. If you know what flow control domain is, good for you. And if you know yourself, also good for you, but that is unrelated to the video. If you don't know any of this, it doesn't really matter. We're going to go through the stuff that you will need in order to follow along. And also, like, if there is something in the videos here that, you know, isn't explained or you don't know it, I mean, I'm not stopping you from complementing the information with additional sources, and I kind of, you know, just pause the video and check it out if there's something you don't understand. And also, if you know all the math stuff that we're going to go through, just skip ahead it, because otherwise you'll just be bored and you will not watch the whole video. So this is the outline that we're going to look through. Why would you need a PID controller? I mean, kind of relevant question since it is about that, and also some of these applications in the industry and domain, right? Some simpler math stuff, and you might want to skip it if you already know it, and then just like skip ahead in the video. And we're going to use vector arithmetics and linear combinations mostly. And also then we're going to do some implementation in Python with a simple game, which was super fun to make. And the code will be provided through GitHub if you want to clone it. But I'll walk through the code and demo it, so it won't be like code along, but I'll go through all the code and show you what it does and demo it, and you know, it'll be clearer at a later stage, I guess. So let's start with the first part, like why would you need a PID controller and some of its applications? Because, as I said, mentioned previously, this lives in the domain of flow control problems. And what that means is, you know, here are some use cases. For example, if you have a building with a heat regulator, so how much heating should there be in the building? That might be a flow control problem. And if you are steering a bigger ship, or you may, you know, you want to be on course with the course that you're plotting on your maps and so on, and that could be a flow control problem in a sense. And how much soda is there in the office fridge, right? There should always be 5 sodas, right? And there might be 3 at some stage and 5 at some stage, which is great, and then 10 at some other state. So basically that could be seen as a flow control problem where we always want to have 5 cans in the fridge. And also, like, if you want to apply this, you need to be able to measure some kind of error. How much off from the optimal solution are we, basically. So in the case of the boat, how many, in the case of the heating of the building, the error here could be how many degrees you are from the optimal temperature. And in the case of the boat, how much drift from the course do we have at any stage? And for the office fridge, it could be, are there around 5 cans in the fridge? So that is how you would measure the error in that case. And also, this might live in a domain where there is external factors affecting this. So for example, it could be bad weather making you drift off course, or you know, going faster and slower and such. And there might be wind fluctuations and current also for the ship, and also like bad weather affecting the temperature of the house. So like if there is snowing, maybe it becomes hotter because of the insulation of the snow, or maybe it becomes colder because of the snow, I don't know. And in terms of the fridge, there might be consultants which are infamously known for drinking a lot of soda, right? So that might be affecting it, since there might be more consultants some weeks and less consultants some other weeks, right? So basically the flow control here is making sure that the flow is correct at all times, and the conditions might change. So that kind of is the gist of flow control problems, and the kind of flow control problems that you might want to use a PID controller for. So let's start with the use case here. I'm going to be using the use case of the course here, RV on course. So let's take a look at this map. What's going on here? So you can see there is something that looks kind of like a compass up here, and it's actually not a compass. It's showing, you can see the arrow here. It is showing the current drift on this particular place in the map. Basically what it says, there is current in the water making you drift off course. And we're going along this course, right, in this direction where I'm moving the mouse. And this is where our front of the boat is pointing to this point, right, and the stern is pointed to this, right. So this is like the desired course that we want to have. But you can see also that the current here is applying force on our port side, the left side that is on the boat, making us drift off course. So we're going here along this course instead, while we actually want to go along this line. And as you can see, intuitively this is not something that we want, right? But the conditions, like the domain, is changing our course here with the drift. So after 1 hour you would actually be up here instead of down here. So ignore this arrow, right? But basically this is the problem, and there are some solutions to this problem. Intuitively, what you feel when you see this is, the first thing that you think is like, how would you do, what kind of actions would you take so that you would compensate for this current that we have? How would you compensate the course so that you would stay on this desired course? And intuitively what you would do is you would steer a little bit to the left, you know, in order to compensate for this drift. So that might be one solution, and there might be other solutions, and we'll see what kind of the problems that will arise if you just do this, right? So the first thing is like, how would you measure the error? So let's say that we are tagging along this course, the desired course, and now the drift from the current is affecting the position of the boat, making it go more north. So we are positioning the boat a little somewhere along this course instead, along this leg. And at any point from this leg, we can measure the distance to our desired course, and seeing how many meters or how many whatever inches, feet, whatever, how much error do we currently have? Basically a proportional error. So we can at any time measure the distance to the desired course here. So you can see here, this is, you have on the x-axis here you have time, and at this time here we measure, at any given time we measure the distance to the point where there will be no error in the case of the boat when we are on course, right? So this is kind of intuitive, the proportional to the desired course. And here is another one, the integral, and what this does basically is kind of doing the same thing, but we're chunking up in, if you could think like chunking up in slices, and then sum up all the proportional errors over time. So basically what that would mean is, let's say that you are maybe at this position here, you would measure the distance, and then you would also use addition in order to sum up all the previous errors that you have had along this line. So like plus 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 of all the proportional errors up to the point where you currently are at. And so basically, if you think of this, like if you would go like in a oscillating along the desired course, it'll look something like the cosine here. And you would sum up the area of all these. So this would be along the negative axis, and this will be along the positive, and plus this area, plus this area, plus this area, and all the sums, right? So that is the integral. So what is the sum of our error, basically, historically? And then the derivative is kind of interesting. So what this says is, you know what, take our position and also take a position in the past, a little bit in the past, like small slice. Maybe if we're going along the undesired course, maybe 5 minutes ago. And then we see we are seeing basically we had an error 5 minutes ago, and now we have an error 5 minutes later. And then you basically take the difference between them in order to get how much our error has changed over time. Basically, the derivative part here saying that, you know, you can see this arrow here. We're taking the derivative at this particular point. You can see that this arrow is kind of pointing downwards towards the optimal solution where there is no error. And that is the derivative at this point. So seeing that, you know, we're going to the right, we're currently doing good because the derivation of the error here is decreasing, is going towards the no error line. And that is all the parts, you know. That is what it stands for: proportional, integral, and derivative, PID, right? So that is the intuition for that. And now let's move on to the quick maths. And if you know this, you can skip it. And if you don't know it, watch it. Maybe it's not going to take that long time, so if you want to tag along, sure, do that. Let's start with the vector operations, because we're going to be doing a little bit of that in the demo. And in Python, and Python 3 I'm going to be using, it doesn't really matter. We're going to be using the NumPy, the NP library. And that has some kind of good stuff where you can do arithmetics like addition and subtraction, multiplication and division on vectors, which is kind of nice. And that is what we're going to do here. And also, like, just a heads up, I don't think you can do this with regular Python lists, and that is why we have NumPy. But this is just like the math, how it works, right? So let's see that we have two vectors here, A and B, and they have 2 dimensions. You can think of them like x and y if that helps you out in a position in a grid or whatever. But they have different values. That's what's important here, A and B. Then the actual values is arbitrarily. If you do addition on them, if you take like A plus B, what you're going to do is you're going to take element pairwise on the same dimensions and add them up. So you're going to take 30 plus 10, which is 40, and that's going to be in the x position here. And then you do 40 plus 20, which is going to be 60 in the y position, or whatever dimension that is. The same thing applies for subtraction. So if you do b minus a, you're going to take 30 minus 10, which is 20. And then you're going to take 40 minus 20, which is also 20. So you're going to have 20, 20. And so that's how you do when you do, and it works the same thing with multiplication. You take them pairwise, and division also. If you want to do, let's say, multiplication, and now instead of a vector here, you have a scalar value, so just like a single value here, in this case, the number 2. So if you take the vector A here, and then you multiply it 2, you're just going to scale them along that axis. So you're going to take 2 times 10 and 2 times 20. So you're going to take 2 times 10, which is 20, right? And then you can take 2 times 20, which is 40. Now we have 40 here. And the same thing applies for division. So if you have A here and you divide by 2, you're going to have 5 in this position. And then for the second position, you're going to have 10. So it's pretty straightforward, right? It's just regular stuff, but doing it by index instead. And now, this is kind of important to understand the demo, like how this game physics here is working. And so I suggest, like, we go through this, and then I suggest you pause the video and work through these examples here, right? So let's say that we have a position here. Position 0, 0 is the top left corner. in programming, that's almost the case all the time. So like 0, 0 is the top left corner of the grid. If you have any position, in this case 10, 20, and then you have some kind of force, in this case 1, 1. The force needs to have the same dimensions as position. In this case, it has 2 dimensions. You can think of them like x and y. And if we apply this force to the positions, you take position times force. And remember, this is vectors, so they're going to be plussed together using addition in this like this, like we did in the examples, right? So keep that in mind. So the new position that we get when we apply the force to the position is going to be 11 and 21 in the grid. So you can have an x position of 11 and the y position of 21. So now you can see that when we apply this force, we have moved in the direction that the arrow here is showing. We have increased in the y-axis, and we have increased in the x-axis also. And we have increased by 1 in both of them. And also what we're going to do in the demo is we're going to, instead of saving this in an intermediate variable, we're just going to do plus equals on it. It is the same thing, but it's shorter to keep in mind. It just has side effects on the position vector, so we don't have to have this third variable here, right? So plus equals the force, that means that we have applied the force at the position, and now it's at a different position. So here are some other examples. So let's say that we want to move in this direction. What does that mean? It means that we decrease in the x-axis and increase in the y-axis. So we take -1 for the x-axis because it's moving to the left, right, which is a decrease in the x-axis. And then we have an increase in the y-axis because we're moving downwards. Remember, the position is 0, 0 in the top left corner. Same thing, like we're going to move in this direction, upwards to the left. That means we are decreasing in the x-axis and we are decreasing in the y-axis. And the last one is we moving to the top right corner. That means that we are increasing in the x-axis and decreasing in the y-axis. And of course, it doesn't have to be 1. It could be any number, right? You can just apply anything to anything, right? The numbers here doesn't matter. What matters is how it moves. If these numbers were greater, the length of this arrow would become longer. So yeah, if that was confusing to you, pause the video, maybe do some experiments with this in your preferred language or whatever floats your boat, and make sure that you know these before you move on, because otherwise you're going to be super confused with the demo later. So check that out, because that is important. And now for the second one is linear combinations. With this, we're going to be, you can think of this like a mixer board, where we mix linearly different variables. In our case, it's going to be 2-dimensional. So we're just going to have 2 sliders on our mixer board, kind of crappy mixer board, but whatever. And it is consisting of 3 parts. We have an input, which we're going to call x. We have some kind of weight that we're going to call theta. And we have some outputs, which is just going to be a variable holding the final score, if you will. The weights here is analogous to the sliders on the mixer board. So keep that in mind if you want the analogy to follow along. So let's say that we have some use case for this. So yeah, we have our mixer board and whatever, and we want to figure out movie recommendations. So let's say that I have some movie preferences. I have some weights. These are the weights, the thetas. So let's say that there are 3 parameters that I am considering when watching movies, and that is the amount of full frontal nudity, the amount of violence, and the amount of romance. And these are in the domain -1 to 1, so they can be anything including these numbers. So full frontal nudity is -0.2. I don't particularly like it, but it's like slightly below 0, which means that with 0 is like I don't mind either or, but it's like I slightly dislike it, right? Violence, I kind of like it. It should be 0.5, and romance, yes, me gusta. There should be plenty, right? So these are the weights. These are my preferences. These are the sliders on my mixer board, right? And now along comes a new movie. It's like, do I want to watch this movie or not? It is also in the domain -1 to 1. So how much full frontal nudity is there in this movie? It's like 0.8, so there is a lot. And there is some violence, but not too much. And there is quite a bit of romance in there, 0.5. So what is parameter here is this? This is theta 1, theta 2, theta 3, and this is x1, x2, x3, and this is for the movie. So now what we want to do is want to figure out, is this the movie for me to watch, right? And I have used parentheses here. Mathematically, you don't have to do it, but I think visually it's easier to see that these are grouped in 3 components like this, if you do it like this. So that's why I have used components. So basically how it works is you take the thetas, you multiply it with the corresponding x value. There should be an underscore here, sorry. Theta 1 multiplied with x1, because it's the same parameter. And then you do the same thing with the other parameters. And then you just use addition between them. And you can, plug in more components here at the end. You can have arbitrarily large amount of them. And if we just put our values in here, and I remove the parentheses here, the score is going to be based on this. So like minus 0.2 times 0.8 plus 0.5 times 0.1 plus blah blah blah. And then if we calculate this, we get some kind of score which is 0.29, which is not a great movie, right? It should be, I mean, it's not worthless, but it's probably not going to be the greatest movie that I have seen. So this is also a good time to pause the video. What I suggest you do is you make this replication of the scoring here, and then you play around with the weights and the inputs to make sure that you understand how this mechanically works, because that is also going to be super important for you if you don't understand how that works. And also it's a really good model to know, because it's used a lot in everywhere. Basically we want to merge different parameters and weight them and so on. And yeah, that's the maths part of it. And for linear combinations, in terms of the PID application, what you do is you pick the weights, the thetas, for each component of the PID. So like the PID, they each have one corresponding weight of how much you want to consider that particular error in the output. And how these weights are picked, that is not covered in this presentation, and that is not something that is easy to pick. That could be really hard to actually figure out what kind of weights you should be using for your domain, right? I think like in general you either allow user input to adjust the weights like in the mixer board example, or you heuristically derive them from some kind of system or whatever, and you try them out differently during runtime or whatever. So they're picked somehow, and that is not covered how they're picked. And then what you do, what you do is you measure the 3 different errors that you get at any position or at any point in time. And what you will get is a vector of errors. For in a 2D world, you will get the 2D vector. In a 3D world, you will get a 3-dimensional vector. And that is true for all dimensions. Now you have these 3 errors. You do a linear combination with the measured errors that you have and your selected weights. So you can see how you can tweak how much proportional error I want to consider, how much integral error I want to consider, how much derivative error I want to consider. And you will get a vector with the force, and then you would apply this force to the controller. And in the case of the navigation that we used, that could be the navigation system, right, for the boat, like how much should you steer port or steerboard or whatever, starboard. And in the heating system, it could be how much hot water there should be in the radiators, or whatever is like the thing that you're trying to control with this PID controller. It could be also sales system, like how much you should charge with dynamically setting prices in your online shop or whatever. So you get a score, basically. That's what you do. You get this score in the end, and then you apply that to something. So that is the theory behind that. So now I'm gonna stop this video, and the next one we're gonna go through an implementation of this in a game. So I'm looking forward to that. Also, don't forget to subscribe if you haven't already, because that helps me to see like what you're interested in and stuff. And if you have any questions or anything, leave it in the comment section below, and I usually answer them like immediately. And I hope to see you in the next video. Bye bye.